In this lecture, we will introduce the concept of input-output stability. And in this context, input is not the control input. It's not something that we can use to manipulate the system, like the voltage that we apply to the terminals of a DC motor. It's not like that. Okay, so its input is here is the disturbance, the unwanted guy. Okay, the measurement noise, for instance, something that affects us in a bad way. And output is the output of the system is something that ideally we want to be zero, or something that converges to zero, like the distance between the actual thing and the to some reference signal. Like you want the room temperature to be 25 degrees, and the output for that system would be the actual room temperature minus 25, and then you take the norm. So ideally you want that to be zero, because when it's zero, then the room temperature is at where you want it to be at. Okay. And so since in practice we can not totally remove the effect of those unwanted guys, okay, negative forces acting on the system, therefore it's meaningful to study, okay, it's worthwhile to study the relation between the disturbance and the output of the system. Okay. So therefore, qualitatively speaking, input output stability is concerned with the following question. So, is the output in some sense well-behaved under well-behaved input? Okay. Okay. And generally speaking, by well-behaved, we will mean bounded. Okay, it's not getting very large. So that's the question: is the output well-behaved under well-behaved input? Okay, that's we're going to try to answer that. And also we will go a step further, and we will try to quantify that well-behavedness, okay, or the effect of the input on the output, okay, through some functions. Okay. So, visually speaking, suppose that this is our system. And then that system is under effect of some negative forces, which we call an output. Here, the input. Okay. And we have the output coming out of the system, the measurements. And then generally speaking, what we want is, we want when the input is bounded, okay, that is, you can find a number such that for all times of interest, it's always the norm of the input. It's always smaller than that number. Okay. And then we want that to result in an output such that the output is also bounded. Okay. And smaller the bound on the input that you can place, you want in general that the output, the bound on the output is also getting smaller and smaller. So, in a sense, what we want is, we desire bounded inputs generating bounded outputs. Okay, so that's something that we talked about in 542 in linear systems. Okay, so therefore, before we introduce the necessary definitions for the nonlinear case, for the general case, let's remember, let's review quickly what the case was for linear time invariant systems. Okay. So we studied that subject, the relation between the input and output under the title bounded output stability of linear systems. Okay. So let's recall that. So bounded input, bounded output stability for an LTI system. Of the form x that equals ax plus du, y equals cx plus du. Here x is the state, u is the input, and y is the output. And once again, by input here in this context we mean the negative forces, undesired forces that are affecting the evolution of the system. Okay, so let's call this system x is Rn, u is in some other space, and y, the output, is yet some other space. And also, in the nominal case, what we want is we want y to be 0 or something that converges to 0. Now, this system, the linear system, is said to be bistable. Is bounded input, bounded output stable if there exists a positive number g such that for a system at rest, that is, you set all the initial conditions to 0, the relation between input and output can be described through the following inequality. We can write sup t is always upper bounded by the supremum of the input signal multiplied by that constant g. Times sup u of t. Okay. For all input functions. From B, we align to R n. Okay. And this sup is, practically speaking, same as max, but sometimes the maximum doesn't exist. For instance, okay, consider 1 minus e to the minus t. Okay. So, this is 1 minus e to the minus t. T is 0. What happens is this signal becoming closer and closer to 1, but it never exactly becomes 1. So we cannot talk about a maximum value because it doesn't have a maximum value. Okay, it's always getting closer and closer to 1, but it never reaches that. And then sup is the smallest number that you can use to upper bound your signal. Okay, for instance, this signal 1 minus e to the minus t doesn't have a maximum value, but it has a supremum, and the supremum is 1. Okay. Okay, so that's but practically you can think this sup as just the same as max. Okay. And now that's the definition of bound input, bound output stability for a linear system. And let's also remember under what conditions viable stability is guaranteed, okay, for linear systems. And then we will move on to after making a review of C modes to the general case for nonlinear systems. Again, from linear systems theory, we have the following. For system 1, okay, for our linear system, we have the following equivalence. Okay, it turns out that to check whether the system is bound input, bound output, stable or not, all we have to do is checking the poles of the transfer function. Okay, in general, transfer function does not have to be a scalar. Okay, it's a scalar when the output and input are scalar functions, but in general, it's a matrix. Okay, so transfer function matrix, and what you do is you check the poles of that matrix, and by poles of that matrix, we mean, since that matrix is a function of S, it's not. Okay, it's not a constant matrix. What you do is you go entry by entry, and each entry will give you a function. Okay, a fraction, a rational function, fractional function. What you do is you check the denominator polynomials of each of those entries, and then for each of those polynomials, you look at the roots. Those roots are called the poles of the transfer function matrix, and if all those poles, okay, are with strict negative real parts, then and only then your linear system is bound input, bound output stable. All poles of the transfer function matrix, the transfer function matrix, which is C times Si minus A inverse times B plus D. Okay, all these matrices, A, B, C, D, they are constant matrices, and this is a function of S, complex variable. Okay, are with negative real parts. Okay, so that's if and only if condition for bound input, bound output stability for linear systems. Now, the poles of this transfer function matrix is a subset of the eigenvalues of A matrix. Okay, and therefore, from this equivalence, we can obtain the result that if the eigenvalues of A matrix are all with negative real parts, then the system is bound output stable. But the reverse direction is not true, because there may be some eigenvalues of A that does not appear as poles of the transfer function matrix. So therefore, that relation is only one directional, unlike the bidirectional implication here. So A with eigenvalues, strict negative real parts, and such A matrices we call Hurwitz matrices. Okay, implies that the system is bival stable. Okay. And then as we said, some of the eigenvalues of A matrix may not appear as poles of the transfer function matrix, and that has to do with, that's intimately related to the concepts of observability and controllability. Okay. Turns out that if your system is both observable and controllable, then all the eigenvalues of the A matrix appear as poles of your transfer function. In that case, under observability and controllability, this relation becomes bidirectional. So if system 1 is both controllable and observable, then under that condition, under that assumption, we have equivalence between those two properties. A Hurwitz is equivalent to Bible stability. Okay, for our linear system. Now, what we're going to do here for non-linear systems is that we're going to start talking about a generalization of boundary input, bound output stability, or Bible stability for linear systems, and that is studied under the name L stability. Okay? So generalization of Bible stability for linear systems is called L. Is called L stability. L stability. Now, before we introduce the definition of L stability for nonlinear systems, let's also quickly review signal norms. The two most important norms that we will study are L2 norm and L infinity norm. They are for signals. So let's make sure that we know what they are. Signal norms. Okay. Now, by a signal, we mean a function of time, and at each value of time, it takes a vector value. Okay. So that's what we mean by a signal. U 0 to infinity to R. Okay. For each value of time, for each time, it takes value of a vector in R. So that's a signal. Clearly, if m is 1, then we're talking about just scalar signals. Now, L2 norm is something that's very closely related to the RMS description of a periodic signal, okay, that we're familiar with from electrical circuits. And the L2 norm of a signal, and this is the notation. Okay, sometimes it's not written if it's obvious what norm we're talking about, but if it's not, you put a small L2 here as a subscript. Okay, so L2 norm of a given signal is defined as this integral. What you do is you integrate the norm square of the input vector at each value for each time, okay, from 0 to infinity, and then you take the square root. ut transpose ut. This is the, if you take u of t as a vector, okay, and then this is the Euclidean norm square of that vector at that particular time t. So you integrate this. Okay. Then suppose that you obtain finite value, and then you take the square root, and that's the L2 norm of, if it's finite, that's the L2 norm of a signal u. Remember the RMS definition of a periodic signal, it was, instead of infinity, you take the period of your periodic signal, you compute this integral, and then you take the average, you divide everything by the period, and that's the RMS value of some periodic signal. And then we have L infinity norm of signal, and the notation that we use is the norm notation, and then as a subscript you have L infinity. And define that as sub of u of t. And here this norm is the vector norm. Okay, you pick a t, okay, and then u of t is a vector in Rm, and then you compute the norm of that vector. And then once that's complete, what you do is you take the maximum or supremum of all those possibilities from t equals 0 to infinity, and the largest value, or the supremum, gives you the L infinity norm of the signal. Okay. And then here, this norm, well, we can take any norm for that, 2 norm or infinity infinity norm or 1 norm. But nevertheless, this is a vector norm. And clearly, depending on which vector norm that you choose to work with, you will have a different L infinity norm for your signal. And then the generalization of these definitions is what we call an LP norm. Okay? I'm just going to put it down because it will not cost us anything to define it, but usually what we do is we work with either L2 norm or L infinity norm. An LP norm is defined as U LP 0 T P. Here P has to be larger than 1 dt, and then you take the pth root of what you compute. P greater than or equal to 1. And one more thing, one more definition. L, P, and then as a subscript you put N. This notation denotes the space of all signals of this form. So this N is the dimension of the space where the value of the signal at each time resides. U 0 to infinity. And with finite, okay, so that's important, finite LP norms. Okay. Now clearly the equivalence between norms that we have for vectors doesn't exist for the signal norms, because you may have consider constant signal, constant at 1, so it has a very well-defined, easy L infinity norm. It's just simply 1. Okay, suppose that unity is scalar. Whereas here, what you have is you're integrating 1 from 0 to infinity. Therefore, the result is infinity. Okay, so you have a finite L infinity norm for a signal, but that may result in an infinite L2 norm. Okay, for the same signal. So we don't have equivalence between the signal norms. So that's something to keep in mind. Now we're ready to start business. Okay, that is, we're ready to introduce stability. L stability. Okay, so here is the definition. Consider the system, okay, nonlinear system. X dot equals f of x u, y equals some other function of, okay, state and the input. And we denote the initial condition by x sub 0. We're considering the time invariant right hand side. Therefore, without also generality, we will be taking the initial time to be t equals 0. And this is x sub 0 is our initial state. Okay, so let's call this system as system 1. Now, the system is said to be LP stable. Okay. If you can find the class K function of K, and remember what the class K function was. It's a continuous function starting from 0, okay, 0 at 0, and it's strictly increasing. Yeah, and that's it. If it's also unbounded, we call it a K infinity function. Okay. But here, for this definition, we require alpha to be a class K only, and for each initial condition of n, there exists a constant which we denote by beta, such that we have the following inequality relation between the output and the input. By the way, this is the output, y is output, u is the input. The LP norm of the produced output is always upper bounded by the LP norm of the input passed through the class K function alpha, and we have this constant beta, which is a function of the initial condition in general. Okay. For the sake of completeness, let's write down what is what, where, why, Q, okay, is the output produced by initial condition x0 equals x sub 0, and the forcing signal, and forcing signal or the input u0 to infinity to Rn. And the system is said to be finite gain LP stable if you can obtain this inequality by a linear class K function. Okay, the system is said to be finite gain LP stable if you can find constant, okay, forcing constant gamma, which would be the slope of our class K function here, such that norm of the output is upper bounded by that constant times the LP norm of the forcing signal, the input, plus the constant term due to the initial condition beta. And the smallest possible gamma that we're talking about, that constant, if its value defined if such a thing exists, okay, is called the LP gain. Gain of the system. Okay, so that's the, in a sense, generalization of the bounded input, bound output stability that we're familiar with from LTI systems. Okay. Now, let's see an application of this definition for the LTI systems, and then we will move on to the nonlinear case. This is our first theorem. Okay. It's theorem 5.4 in the text. Consider the LTI system, linear time invariant system. X equals ax plus du. Why is this cx plus du? Where system is exponentially stable in the sense of Lyapunov, meaning that A matrix is Hurwitz. All the eigenvalues are with strictly negative real parts. A is Hurwitz. Okay, so therefore this system is bound output, stable. And let's construct the transfer function for this system that g of s c si minus a inverse b plus d. The transfer function matrix of the system. The system is L2 stable. Okay, with L2 gain that can be directly computed from the transfer function. L2 gain given as gamma is supreme omega VR. Okay, it turns out that all you have to do is you have to check the values of g of s on the imaginary axis. G, J, omega. And then you have to look at the 2 norm. Now, G omega is a matrix, okay, in general, unless both input and output are scalar signals. And what we do is we check the 2 norm of, the induced 2 norm of that matrix. Okay, so this is for all values of omega. This is induced 2 norm. In other words, we're talking about the largest singular value of this matrix. And then you take the largest of all those largest singular values, and that's your L2 gain for this linear system. That is the largest singular value of G of J. Okay. Now it's not easy to visualize what's going on for the general case. Okay, for input and output, possibly vector value functions. Okay. However, for the single input, single output system, where the transfer function is a one-by-one matrix, in other words, when the transfer function is scalar, then the Borel tells us the L2 norm, or the L2 gain of this system. Let's put that down as a remark, because it's a very nice and simple observation. For a single input, single output LTI system, system with system matrix that's Hurwitz, okay, with Hurwitz A matrix. The L2 gain can be read from the Borel plot. Which may become a useful information if, for instance, you don't have the system model. Okay, you don't have the model for it. All you have is, let's say, experimental data plus the fact that you know somehow that the system is linear, or at least it can be modeled in an accurate enough way by a linear system, then what you do is you perform a frequency sweep, obtain the body plot experimentally, and then the peak value of the body curve gives you the L2 gain of your system. Okay. This is omega, this is GJ omega. Say, and then suppose that we have something like that, sort of like a bandpass filter, and then this peak is what the L2 gain of your system is. Omega 0, let's call it. So this is the peak of the body plot. Okay, and that peak is your L2 gain of your system. Okay, now let's move on to the general case of nonlinear systems. Theorem 5.3 for the text. Consider the system x dot equals f of x u. The output is defined through the function h. Let's say 1 f locally Lipschitz. H continuous. Suppose the following conditions hold for the system. Okay. One of them is the system is input to state stable. Okay. That is, the norm of the state can be upper-bounded by class KL function that represents the effect of the initial condition system and class K, and the norm of the input passed through some class K function. Okay, so suppose that system 1 is input to state stable. Furthermore, suppose that there exists alpha 1, alpha 2, both class K functions, and a non-negative constant that we call in eta, such that h of x of u. Okay. So this is the norm of the output for some particular x and particular u, because h is the function that appears when we define, when we describe the output. Okay. This is upper-bounded by norm of the state passed through the class K function alpha 1, norm of the input passed through the second class K function alpha 2 plus eta. Here this x and u, they're not x of t and u of t, they're just vectors. Okay, the vectors that appear here, they're not signals in that sense. For all x in Rn and u in Rn. Okay, for all x and u. Then our system has to be L infinity stable. System 1 is L infinity stable. Okay. And the proof is quite straightforward. All we have to do is we have to just invoke the definition of L infinity stability and input state stability. And with a very tiny trick, we will obtain what we claim. what's been claimed by theorem 5.3. Here is the proof. Okay. Let's first remember the definition of input to state stability. Input to state stability implies that norm of the solution, okay, of the system x of t can be upper bounded by beta function. Okay. Remember, this is a class K function that's non-decreasing with respect to its first argument. Okay. And right, when the 0 at 0 and non-continuous and non-decreasing with respect to its first argument, when the second argument is held fixed, and when you fix the second argument, first argument fixed, then it's non-increasing and converges to 0 with respect to the second argument. Okay. Plus the term that describes the effect of the input, sub tau t norm of input. Okay. And this inequality is uniform in the sense that this class K function and that class K function, they are independent of the initial condition and also the input that you're driving the system with for some beta class K function and gamma class K function. Okay, so that's the definition of input state stability, and we assume that our system is ISS. So let's, starting from that definition, let's obtain L-infinity stability for this system, provided that the function that describes the output satisfies this inequality, okay, for all x and u. Okay. Now, suppose that we have chosen an initial condition and we have chosen some input, or input is given to us, and then from that initial condition, under the influence of that input, we start the system, and the system produces some state, okay, the solution of the system, and then that state passes through h function together with the input passed through the h function. They produce the output of the system, y of t. That's our signal in our Q. Y of t. And then this is less than or equal to what? Using the second condition, we can use the solution and the input signal to upper bound the output. Okay. So alpha 1 of norm of x of t, and norm of x of t is upper bounded by that class K estimate and the class K function gamma. So we have that beta term and we have the gamma term. Okay, inside beta we have this, and inside gamma we have that supremum of the input. Plus we have the second class K function alpha 2, and that includes the norm of the input, okay, at the particular time t. And plus we have the constant A, okay, that comes with that condition. Then this is less than or equal to alpha 1 2 beta plus alpha 1 of 2 gamma. Okay, by 2 beta we mean this term here, beta is a function of norm of initial condition and t. And here gamma is a function of supreme of the input norm, plus alpha 2 u of t plus eta. Okay. Now the question is how we move from this line to that line. What we did use is here. We use the fact that alpha 1a plus b can always upper bound it. by alpha 1 of 2a plus alpha 1 of 2 times the other argument. Okay? So it's a very nice, very short exercise to figure out why that is the case. It directly follows from properties of class K functions. Okay, 0 and 0 continuous and strictly increasing. And then we can write that's less than or equal to. Okay, so what we're going to do is we're going to collect the terms that contain the input. Okay, we have this term, alpha 2 term, and we have alpha 1 of 2 gamma term, because gamma inside gamma we also have input. So let's gather the input terms and then collect other terms as next piece, next chunk. So what we have is alpha 1 of 2 gamma. Then we have supremum tau from 0 to t of the norm of the input. Okay, so this term we're talking about. Then we have plus alpha 2 of norm of u of t. Okay, and then this norm of u of t clearly can be upper bounded by the supremum of the norms from where the supremum is figured out from 0 to t. Okay, so that's an easy one. Supremum tau from 0 to t u of tau, because this thing is clearly never smaller than the value of norm of u of t. Okay. So that piece is where we collect all the input terms plus alpha 1 of 2 beta x of 0 comma t. Now since it's not increasing with respect to its second argument, therefore this thing is always upper bounded by the value of that function at the smallest possible t, which is 0. Therefore instead of t you can put here a 0, so that becomes a constant instead of a function of time. And plus eta, which comes from this assumption here. And we're done. How is that? This two terms we can use to define the class K function, which we call it gamma 0, class K function of supremum tau in 0 to t u of tau. And this thing, note that it's not a function of time anymore, it's constant. Together we can call this thing to be the constant beta 0 that appears in the definition of L stability. Okay. Therefore, with our new notation, the L infinity norm of y of t always less than equal to gamma 3 plus beta 0. Here this is the value of the output at some particular time, but going from this this norm for y of t to L infinity norm of the signal, it's an easy logical step. Therefore this thing is the L infinity norm of y is upper bounded by the L infinity norm of the input passed through function gamma plus constant that comes from the second chunk in our inequality. Okay. That's the simple proof of this theorem, where we basically use definition of input state stability, okay, definition of L infinity stability, plus a very simple property of class K functions, which we use to go from this line to the next.